Hi, I'm Ardavan Modarres, Master Student of Electrical Engineering, and in this video we are going to review MLP-Mixer Architecture, which is developed by Google Brain team and is proposed for computer vision tasks. The outline of this video is like this. First, we do a quick review of the paper and mention key points and ideas. Second, we investigate the architecture in depth, and finally, we implement it from scratch using PyTorch and train it for a few epochs on Cypher 10 dataset. As you know, CNNs have been dominant architecture for computer vision tasks, and also emerging transformer-based architectures in computer vision domain have shown promising results. MLPs are not appropriate choice while working with images, but MLP Mixer, which consists of only MLPs, is designed in a way that not only can learn good representation from images, but also achieve great and competitive results to CNNs and transformer-based architectures. At first, input image is divided into patches, and the first layer of the architecture is patch embedding layer. Then, a couple of layers consisting only of MLPs are applied. Don't worry about patch embedding layer right now, I'll explain it to you clearly later. MLP Mixer should be pre-trained on large datasets and be fine-tuned on your task. Since dimensions of fully connected layers in MLP Mixer is independent from the number of patches and patch size, the computational complexity of the network is linear in the number of patches, unlike VITs whose complexity is quadratic. And overall complexity is linear in the number of pixels, just like a typical CNN. Unlike VITs, MLP Mixer does not use position embedding, since token mixing MLPs are sensitive to order of the input tokens. Don't worry about token mixing MLPs, I'll explain it to you clearly later. Okay, let's investigate the architecture in depth. As I mentioned earlier, the first layer of the network is patch embedding layer, and patch embedding layer is nothing but sliding a convolutional kernel on your input image and map it to an embedding. Let's consider the input image is something like this, and the size of the input image is C by C. And your patch size is P and C is divisible by P. So you can divide your input image into a number of patches. And the patch size is P by P. And by sliding a convolutional kernel like this, we can map each patch in the input image or in the input tensor to a scalar value in the output tensor. So by sliding this convolutional kernel, for example, on this patch, we can map it to this scalar value in the output tensor. And this patch will be mapped to this scalar value in the output tensor, and this patch will be mapped to this scalar value in the output tensor. And the shape of output tensor is C divided by P, C divided by P. And C divided by P to the power of 2 is the number of total patches. Okay, let's investigate more in depth about shape of each tensor. Let's call input tensor to the network X, and the shape of X at first is something like this. Batch size 3, C, C. I'm sorry, let me correct this. C, C. Since we are working with RGB images, the input channel to patch embedding layer is 3. And first, input tensor X goes through patch embedding layer and let's call the output of patch embedding layer X again. At this stage, the shape of output of patch embedding layer is something like this: batch size, number of channels, C divided by P, C divided by P. And the paper states that the output shape of patch embedding layer should be something like this: batch size, C divided by P to the power of 2, which is number of patches, and number of channels. Let's call the number of patches S and the number of channels C. So at this stage, the shape of output of patch embedding layer should be something like this: batch size S, C. So we should do a transformation to convert this tensor to this tensor. Okay. The output of patch embedding layer then goes to mixer layer, and mixer layer consists of token mixer and channel mixer. Okay. First, X goes through token mixer MLPs. Before passing X through token mixer MLPs, we should transform the shape of input tensor X. We apply transformation T1 on input tensor X, and we call the output of T1 transformation Z. At this stage, the shape of Z is batch size C, S. Then Z goes through token mixing MLPs, and let's call the output of token mixing MLPs Z again. Then we apply transformation T1 again on Z, and let's call the output of T1 Z again. And the shape of Z at this stage is something like this: batch size S, C. And since we had skip connections, the total output of token mixer, which we call it X, is Z plus X. Z is the output of token mixing MLP, and X is the input to the token mixing MLP. Okay, so it was token mixer. Then the output of token mixer goes through channel mixer or channel mixing MLPs. So X goes through channel mixing MLPs, and let's call the output of channel mixing MLP Z. And since we had skip connections, the total output of channel mixing MLPs is Z plus X, and Z is the output of channel mixing MLPs plus the input of channel mixing MLPs. And we should apply this module according to the depth of the network. So we should apply it according to the depth of the network. And this is channel mixing MLP or channel mixer. Okay. So at this stage, the shape of X is something like this: batch size S, C. Now we should do a normalization, layer normalization on X, which doesn't change the shape of X. And now we should take mean of X along, for example, patches axis. As I mentioned earlier, the shape of X is something like this, and this is a tensor. We should actually, this is a matrix. These are the features for each sample uh, in this batch, and we should transform this matrix to a vector. So we can choose different ways for transforming this matrix to a vector. For example, we can transform it to something like this: batch size S times C. But it's not a wise choice because the number of parameters will be very large. So we can take mean along one of these axes. A wise choice is taking mean along patches axis or along S axis. So we take mean of X along axis 1, and then X should goes through a classifier head. Okay, X goes through a classifier head, and the output will be something like logits. Okay, I think we are done. In the next video, I'll implement the architecture from scratch using PyTorch, and it will be more clear.